where our hydraulic facilities are located. So I just added from a presentation of yesterday this picture, as we have some things connected with what we have seen yesterday, some experiments with vehicles in floods, intersection of flooding flows, and I will present now the interaction between obstacles and the flow. So what can be the obstacles we consider? For us it was first bridge piers in supercritical rivers, stepped river, as we can find them in Chile, for example, or here in the Réunion Island in the Indian Ocean. It can be street furniture, houses, cars, buildings. We just have seen some examples before, in floods and also in tsunami. So here tsunami, well, we would consider the inland flow. In fact, the wave has reached the shore and this is on the horizontal part of the land where we can have a flow. We saw it yesterday in different presentations for several minutes or an hour. And the inland flow can be supercritical as it is reported in the literature, for example here in Sendai or in other countries. So now, what about what is the supercritical flow? Maybe I have just to reintroduce the Froude number to characterize it. Froude number is an adimensionalized number that is in fact the ratio between kinetic energy and potential energy of a flow. But we can see it also as the ratio between the velocity of the flow and the velocity of disturbances, gravity waves. So it is the velocity of information. When we have a supercritical flow, the Froude number is higher than 1, and so the flow is faster than the information. So you cannot take into account the presence of an obstacle. Transition to a subcritical flow, which is slower than information, is necessary. It is ensured by an hydraulic jump, and in this case, a detached hydraulic jump. This structure, the jump, increases the depth of the flow, dissipates also energy, and transfer energy from kinetic to potential. When we have several obstacles, it can be the mounts used, for example, for rapid flows. The situation is very similar to the one of supersonic flows around bluff bodies. In this case, it's not a jump, but a detached shock wave. So we wanted to take benefits from this analogy, as the description of shock waves by analytical models was made successfully in the 40s with very good results. So here we have a top view. The obstacle is there, so like this. We have the flow coming. So we have the supercritical flow. That can be the inland flow of the tsunami. And if we see the flow, it passes from supercritical to subcritical regime through the jump, and then reaccelerate to this minimum section, and then passes again in supercritical regime. So the zone affected by energy dissipation, by the increase of the water depth, is characterized by this length, for example, the entry length in the shock in the jump, or alternatively by the detachment length of the jump that we will consider in the sequel. So we want to have a model for this length. For this, we use only a mass balance, so the inlet mass is the same here as the discharge outing from this control volume here. With basic laws of the jump, we can deduce the property of the flow as function of the properties of the inlet flow, depth, Froude number, velocity, etc. And we can deduce by energy conservation the flow in 3 as function of 2 and then of 1. And so with this different equation, we can have the value of the detachment length only as a function of the inlet Froude number. This is a very long equation, but we have only parameter. So with this model, maybe we can have an estimate of the length of the jump for every scale, laboratory scale or fit scale. But maybe we have scale effects, and in fact, I have to speak about some assumptions. First assumption of the model is that the jump has no thickness. This is completely true for shocks. They are about 1 micron of thickness, but the jump has a thickness of about the water depth. So with our flows, it's about several meters. Second, and more important, is the horseshoe vortex that was not considered. So here we have a side view of the flow. So we have the incoming supercritical flow. We have an increase of the water depth through the jump. And then we have the impact, the stagnation point. And we see that the pressure here will be higher than the pressure here. So pressure tends to push the flow in an adverse direction, creating a flow separation and a dead zone. In fact, this dead zone is three-dimensional. We have the so-called horseshoe vortex. This structure is very important for scouring, but also has a feedback effect on the jump, as it modifies the actual ground that is seen by the flow. So we have two assumptions, maybe a structure that was not taken into account in our model. And so to see if the model is still valid, we had to perform some experiments. For this, we use this setup. It's a small water table, 1.2 meter long, 0.75 meter wide. We can vary the discharge, the slopes, to obtain different depths and, most important, different fluid numbers. Reynolds is always turbulent, and we can also modify the width of the obstacles that is made by an assembly of small PVC square plates, see, from 2 mm to several centimeters, so the width of the obstacle are. We want to characterize the detachment lengths of both the hydraulic jump and the horseshoe vortex. For this, we use some photographs from below. Okay, so well, we are below the table, so we have a camera, and so we can see here the reflection that show us the two of the hydraulic jump. And here, by releasing some paint, we can see the separation of the flow and then the horseshoe vortex. Okay. So we obtain such results. For example, I have the detachment length of both the jump and the horseshoe vortex as function of the obstacle width. We see that when we increase the width of the obstacle, we increase the jump detachment and also the horseshoe, but the horseshoe vortex is hardly affected. This is in good agreement with our model, qualitatively, but when we compare the results from the analytical model to the experiments, the agreement is not good at all. We see, for example, that in our model, the main parameter is the fluid number, but in experiments, we have a very small dependency to this parameter. More, the detachment length of the jump should not depend on the width of the obstacle, and we see that there is very strong dependency. So we have a very strong discrepancy between the model and experiments. I have proposed two causes, the thickness of the jump and the horseshoe vortex. To decide what is the cause of the discrepancy, we have performed some numerical simulations. So for this, we use commercial code star CCM plus with three-dimensional Reynolds average Navier-Stokes equations with a standard K-epsilon model. We use the volume of fluid method to track the free surface. And you have here control volume, so the obstacle is there where we have no fluid. Wall here, symmetry plane. Here we can impose both the water depth and the velocity, so the fluid number. But what is very important is that on the bottom, we have adopted a slip condition. So we have no friction, so no boundary layer, and so no flow separation. So we have exactly the same condition as in experiments, except that we will not have any horseshoe vortex. So you have here an example of reconstruction of the free surface. We see the two of the hydraulic jump. And the results are presented here. So we see that the green points for the numerical simulations do not match with experiments, but they match better, really better, with our theoretical model. So in fact, we had a theoretical model with no jump thickness and no horseshoe vortex, numerical simulation with a thickness for the jump but no horseshoe vortex. They match very well, and the horseshoe vortex is responsible for the discrepancy, for the failure of our analytical model. It's because of, well, it affects the hydraulic jump by modifying the ground, well, the actual bottom of the bed seen by the flow. But that's not the only problem we encountered during this study. We have also found another flow type that we called coincident. In the previous slides I have presented, we're facing to what we have called breaking type. In fact, when we have a supercritical flow, turbulent, we had an hydraulic jump always located upstream from the horseshoe vortex. So breaking first, breaking type. When we add some additional disturbances, it can be, for example, a point gauge, which is the same with my finger, about 10 times wider, or by removing some settling devices, we obtain this, what we have called coincident type, because the horseshoe vortex, the two of the horseshoe vortex, moves upstream and reach the same location as the one of the hydraulic jump. This is confirmed by additional measurements. Again, we have the detachment length as a function of the width of the obstacles. And we see that position of the hydraulic jump, in red for the first measurement, is not modified in coincident type, but the horseshoe vortex that was located here with additional disturbances migrates upstream and is located at the same place as the horseshoe vortex. So we can say that in this case, with disturbances, it's the hydraulic jump that rules the flow, as it can impose the location of the horseshoe vortex. So as a conclusion, we'll say that we wanted to study the detached hydraulic jump in front of obstacles that can be building in high velocity flows, but the horseshoe vortex prevents us from using analytical modeling. We have identified a new type, coincident type, that is caused by upstream disturbances. And in this case, it's interesting to see that the horseshoe vortex can impose its location to the hydraulic jump, impose the location of the horseshoe vortex, and maybe also of the initiation of scoring around the obstacles. As prospect, well, why don't we use numerical simulation? We use very simplified simulations because the modelization of the horseshoe vortex is really a challenging task. It's very difficult. It's a three-dimensional flow separation. And we have also to model the free surface. So it's very difficult. Quantitative validity is questionable. And, well, it would be interesting to find partners to do it. You intend also to perform new measurements in a new water table, completely made of glass, to be able to perform velocity measurements inside the structures. We must perform larger scale experiments. Why? To see if at a high Reynolds number, the turbulence can, by itself, initiate the coincident mode. Or in other words, if turbulence can replace artificial disturbances. All the way, well, we did not study the scoring around these obstacles, and what is more important is that we have an obstacle, but we study what happens upstream, but not the wake, where is located the zone we want to protect. So it's in the future. Thank you.